So let's get started. So today's goal is to finish the random variable, which is something left over, and then we'll go over some Excel. So I think you have seen that already. The assignment 2 is already there. So I mean, there will be 2 weeks from now. So we finish today. So, and I think the quiz 3 should be there once the TA get it ready, but it should be all there. So let's get review a little bit what we have done since I think not met for a week. I mean, at least a few days though. Probably after the holiday, you hike for a while, then probably I don't still remember. Because after this class, we'll conclude half our course, because after that we'll talk about inferential statistics. So the main idea that we are looking at is consider the world that we study involve numbers, right? Or we can say you can use number to describe the uncertain world, right? Or we look at the world where we're able to measure, and the number is something we care, right? Which often the case for financial market, for insurance company, for accountant, for marketing manager, so on and so forth, right? The number we care. And that's called random variable, right? Basically, you are assigning numbers to outcomes, and of course, you can always assign number to outcome. But the problem is whether the assignment is it meaningful or not, right? The number comes out is meaningful, right? For example, we have this assigned number of head, right? That would be meaningful if the number of head is actually related to your performance, same as if you total contract, the same idea. Okay. So so we have two distinction is depend on what number you can assign, right? If discrete, then it's an integer usually, right? When you talk about continuous random variable is like real numbers that you assign, right? It's rather standard. And then we talk about when discrete, you can describe either big P or big F, the same thing, right? Graphically, just like this we have done many times already. And the two important thing, if you want to summarize big P, is by expectation, right? Same as the mean. And how accurate the mean is the variance, right? I think I'm not going to go step by in detail because I think we reviewed many times already. And this also extends to the case where more than one random variable, right? In our class, we focus on the case where variable independent, right, in terms of calculation. In that sense, that means that sum of the mean will be, right, mean of the sum, right? Variance of the sum will be sum of the variance, okay? So that would be the idea. But as you know, that would not apply when you talk about financial risk, right? As we've seen in this particular example, the bottom one is the variance of the sum will be sum of the variance plus covariance, which is saying that where the last term correspond to the diversification idea, right? If two assets have very low covariance, which that means that you want to diversify, right? That is maybe you can keep the voice down. I'm sorry. So for discrete case, we have 5 different distribution. Particularly, I want to point you to the case of binomial because this is the most useful one. We said you have n different trial, and each trial is either success or failure, and the same is independent, have same success probability. You care about number of success, right? Which is often 5 application there. And particular case, if you apply it to time horizon, they will become a Poisson, right? Poisson, but the case where you try to model how many event would happen within the period of time, right? And Hypergeometric is talking about what we call sampling with dot replacement, right? All of big N objects, A of them are good. How likely that if you draw N object, X of them are good. So that would be the idea. Okay. And after that, we go to continuous random variable. Okay. The first big thing we talk about is small f, small p. The big P is undefined, right? Because you can't say for each value of X what's the probability because they're all zero. So that we call the big F. And big F is well defined, and then by the mean value theorem, you can define small f, right? That is by calculus. If f is defensible, you can always define f. Okay, so happen to be a special case, and we all usually assume our distribution is a nicely behaved, so small f always exists, right? But do note that existence require a smooth property of f, which called differentiable, but that is applied to every case we study anyway. So there's rare case we study the case where it's not continuous, not defensible. That will be very weird. And the main thing that we need to remind you is f is the most useful one, but in terms of calculation explanation with small f, right? Which in that case is the area under the curve will be the thing. Area is the probability is defined. Okay. And we can define expectation in a very similar way. So I think we actually stop somewhere in the normal. We haven't finished, but we'll finish, right? So I think just a quick review of exponential, just to remind you that exponential is used to model when things would happen, right? In the Poisson setting, right? Consider the case of Poisson, right? Where exponential time it takes before the before event happen, okay? And the proof I'll omit, but I don't think even I do the proof here, but you can, if you check further, there will be proof, okay? The next we talk about bell curve. That is the most common used one, which we'll explain 2 weeks time why this is the case, okay? That's called central limit theorem. And particular, you notice that we have a familiar parameter mu and sigma square, which is the variance and standard deviation. Sorry, variance and mean, right? And we learned that a very useful thing is for normal, for the bell curve. And the bell curve has special property. One of them is when you multiply and add by constant, it still remains normal. Do note that it's only true for normal. Most of them are wrong, right? Suppose you add any number to Poisson, it's not Poisson, because Poisson is from 0 to infinity, right? Same as exponential. When you add something, it's not the same, right? Same for uniform. Uniform is multiply, it's not the same. Will not be the uniformly distributed again, right? So most of the things we learn doesn't satisfy this. When it's normal, you do anything, it's still the same, okay? Because of that, then we can always normalize any normal to 0 to 1. That allow us to look at what we call standardized or standard normal. And last time we learned that gives you the set table. You can look at 4 different tables, or you can either 2 of them will be fine. Okay, I think we go over all these tables, so I'm not going to repeat myself on that. Okay, so actually this would imply a lot of time you learn from the management literature talk about the 2 sigma rule. It's like this, or 2 sigma, 3 sigma rule. That is following from the bell curve. Okay. And the very last thing to talk about inverse normal, right, is to ask us, if you give me the probability, I want to ask the value of the bell curve located where such that this would be satisfied, right? So I think we talked about that as well last time, okay? And we talked about how to calculate that, right? That is the last thing we cover, right? And in this, will be the same, right? If you have more than 24, that how it apply is when the inequality you can subtract both sides from 20, the inequality is the same, and you divide the positive number on the both sides, the same statement there. And because the left-hand side is a standard normal, you can look at the table. So basically, you transform the populist statement, which is x more than 24, is same as z more than 1, right? Because mean is 20, the SD is 4, right? So x is more than 24 means that it is more than the number by 1 standard deviation, right? Same as this one. I'm not going to talk about the same as that, okay? You will do the assignment, so you shouldn't be something difficult. So I think I want to draw your attention to this one because we do not need them now, but we will need them when we talk about hypothesis testing, two sample tests. Okay, this is something we will be need. So this is very simple. Okay, we consider a case where we have two bell curves and two bell independent. Okay, you will see that I see independence because we're drawing samples. And the idea is that if you combine two bell curves, if they're independent, that's very simple. The mean just add up, the variance just add up. Okay, that is not something new, right? The mean add up, the variance just add up. Hold true if they're independent. The only thing new in this statement is you combine the two bell, it remains bell. Oh, that's the only new thing, right? Because remember, expectation of the sum is sum of expectation, regardless of independent or not. So that is nothing new, right? So what I meant is this part always true for anything, right? If I have give you this is the mean x, this is the mean y, they must be mean is the same. It's no different. And I tell you independent, the variance is still just add up, right? Variance, sum of variance or sum is sum of the variance because that is the idea of the variance, right? If they're independent, right? Of course, if not independent, you have to add two covariants. Okay. The only new thing is you add the two bell, it's still the bell. Right? So this is a very surprising result because usually it's not the case, right? If you add two exponential, of course, it's not exponential anymore. Two binomial is not binomial, right? In general, right? It depends on, right? But in this case, it turned out to be very surprising. And then two normal is still normal, okay? So if you look at this is a very special case. It's like you have a one normal curve, the other normal curve. You add them up, it's still a normal. And actually, this doesn't surprise you that much because, right, when we said, right, IQ, weight, everything can be a bunch of bells, right? Because we say our height is a result of many, many different factors add together. And each factor may be come up with many, many sub-factors and sub-factors and so on and so forth, right? Maybe you can say our IQ is nature and nurture, right? If you want the bisection, right? And nature can be depend on many things, right? Maybe depend on your parent genes, so on and so forth, right? And nurture depend on what you eat, right? And then what you eat is more like random, depend on today what you eat, yesterday what you eat, so on and so forth, right? So it's two companies of two bell. And turn out two bell is also gives you the bell. Fair. The next one is also related, okay? Turn out to be if two bell you subtract, it's still a bell. Okay, just the mean is the difference, right? It's not surprising at all. The only surprising is still a bell, right? The middle one, the mean is the difference, the same. The variance, the sum, the same, right? Because that is not surprising. The only surprising is still a bell. So it add us idea, right? Because IQ, right? Maybe depend on good gene and bad gene, right? Something is promoting your growth, something is depressing your growth, right? Same as for nurture part, right? Whether if your height depend on whether you jump a lot, right? Or whether you just sleep a lot, not doing any exercise, right? That's a promoting factor, right? Or what we call the push and pull factor, right? So in business world, so that actually the two bell, no matter you add or subtract, right? So still mean a bell. Okay. So this part we will using it later. So just bear in your mind. I mean, we don't need it until then, but just let you know there's something like that. Okay. Now we come to the we may name there 3 more distributions. We don't need them until then, but I just need to introduce them at the moment because you will not be surprised for the rest of the semester. Okay, so here just introduce. If I introduce later, then you can look it back. Okay, and the next one is called chi-square, and chi-square is not used in our class at all, but you'll be defining something later. And do note that chi-square would have its own uses, but in our class we don't. But if you look at textbook, they will tell you how to use chi-square, but in our class we don't use it. Okay, the idea is very simple. Chi-square is simply chi is a typo. Actually, it's x squared. Actually, x actually corresponds to z. It's z squared. Okay, a standard normal square. Okay, chi-square means very simple. Simply means the following. Maybe I draw a graph to make sure that you understand what's going on there. Okay, now I have a standard normal. Okay, and a bell curve, right, which have mean 0, variance 1, right? This is what we call standard normal, right? Everyone knows it. This is standard bell. Okay, every normal you can always reduce to this one. Okay, now the question is, we are not interested in the normal itself. We're just following. So I just roll a die. Nature tell me this number. Okay, but I'm not interested by this number itself. I'm interested in number square. Square this number. Okay, and as you can imagine, this is called the chi-square. Okay, and what it means is everything 0, right, will remain 0, right, and everything that is negative will become square, right, will become positive. Okay, then turn out to be something like that. All right, and that's called chi-square. Okay, the number that I got from the bell I squared. Okay, and because of square, it starts from 0 to infinity, right? Because right, so that is all I have. Okay, that's called the chi-square. Okay, and I only have one of them that is called chi-square of 1. Okay, and probably ask, I have 1, then must I have chi-square 2, 3 and 4 and 5? That's very simple. Chi-square of 2 means that I close my eye, I take one number here, I take one number here. Okay, and I square them separately and add them up. That is called chi-square 2. If I chi-square 3, that means I close my eye, draw some number from the bell, square 3 of those, add them up. That's called chi-square 3. Okay, so you'll probably ask what it is. This actually we relate to the variance idea, but we will define it carefully later. But that is chi-square. That's what you need to know, and that is what we will define later. Okay, but at the moment, I'm pretty sure that you don't know why we are doing that. Okay, but later we will define. But let's define what they are, right? It just add them all up. It's just chi-square. Okay, and we don't do any proof, but just telling you what it is. Okay, just close your eye and draw a number and square, and note what it looks like. Okay, and if you really care about the shape, it's similar to that, right? Chi-square will look like this, and 3 will look like this. It's like more bell curve. And actually, you can see that if chi-square to the infinity or big N is like a bell, okay, it's very closer to normal. Okay, but we're not going to say anything about that. But is that okay? Okay, just definition. Nothing. There's nothing to learn here. Just I tell you this is the case. We'll tell you how to use it in the future. Okay, it's just like a thing you know. Okay, but don't worry about that. We're not asking you for assignment at the moment. Not the quiz or whatever. So it's just put it there. We'll come back later. And also, things will come back later is the other one is called the T distribution called student T, actually mentioned. Okay, and later you understand why they call student T. But T is a rather funny thing. You notice this very weird. It's funny. It's like there's a fraction, and the numerator is a standard normal, the bell, You draw a bell there. And the bottom is even more funny, is you draw M standard normal. Each of them is square, add them sum, that's a chi-square. And you divide it by M again, how many of them you draw, and take a square root, okay? Very weird thing, okay? Very super weird, whatever you say, it means very weird. And depending on how many you draw, the denominator, I got the T to the degree of freedom M, okay? And you ask, okay, what is, okay, very weird, super weird, okay? And the first, I would first convince you that this is, T will be something you use it throughout our course, okay? When I say normal, that one is very close to normal, okay? And actually, when M go to infinity, it's actually same as normal, standard normal. And we use this one throughout our semester because we can't use the bell directly, okay? Bell is something, in theory, it works. T, this one, is something when we collect sample and we apply this one. Okay, of course, later you will see when the sample size is more than like 200, that the bell and the T are the same. Okay, when M is close to 200 or above, which usually you would do for your data, there's no difference between the bell and this T. Okay. To make you feel more comfortable, how it looks like T is like the follow, correct? It's like the bell, but it's like a pressed bell. So you have bell there, you press a little bit at top, that is the bell, that's the T you have, okay? And you can see the T to the 1 is the red one, more and more depressed. But when you having a bigger M, actually later you see M is the sample size. When you increase the sample size, or then you will tilt up this, depress the bell, and then higher and higher, higher until it become a bell, real bell shape, okay? And for the moment, I'm pretty sure you don't understand what I'm talking about, but just give you an idea what the T is. Later, we'll talk about that. So let's give you an idea what we're doing for the rest of the semester. So then you have no surprise. So basically, once you learn all this chi-square, T, and F, which we'll talk about immediately, then there's no more new distribution anymore. Okay? T, okay? Student T. And the last one to talk about this is, again, something that you would find very weird. I agree, if you first learn it, there's no reason we learn this, okay? Why we care about all this, but later you will see why we have that, okay? But that is very simple. It's a 2 raised of chi-square. The first one is chi-square degree M. The other was chi-square degree N, and divided them by how many degree of them, and then this called Fmn, okay? And you ask, okay, what are we doing there? Later you will see by the early of November, you know what it is. That is when we use it to compare variance. Okay. Well, I want to compare the variance of one group is bigger than our group, which is we'll use often, right? We want to say whether men have more variation in earning compared to women, right? Or particular say or variance comparisons stock market, right? Is a particular stock have more risk than the other one, that we use F test. Okay, so that will be something that we will keep using all the time. Okay, compare variation. Okay, and T will be probably compare mean, right? Later you will see F is compare variance, right? T is compare mean, right? I have 2 sets of data, 2 different stocks. I want to look at the data if particular stock has higher return than other. That is, I compare mean. Or I have men and women's earning, is men making more than women, right? That is where I use T. Okay, and F is compare variance, whether the risk of 2 stocks are the same or not. But don't worry, this will be covered later. I just introduce it now because it's good to put it here rather than when I talk it, I bump out something new. I mean, of course, I bump out now, but no matter where I bump it out, you will complain anyway, because this is a time where we don't give you any explanation, okay? Because it's way beyond the level we talk. But you notice that is the F is looks like either like exponential like this, or like chi-square, like chi-square. Depending on the M and N, it's just like going down or up and down. Okay, there's only 2 different shapes, and don't worry. These tables, you check table anyway at the end. Okay, so you will, at the end of the day, this is basically all the math technique that we require. Okay, you will do for the rest of semester, mainly do binomial, normal, T and F. Okay, these are the four things that binomial, normal, T and F. Yeah, that's the four things that we will cover for the rest of the semester. Okay, and I hope you feel comfortable so far. We have talked. Okay, then what remain for this class we'll talk about is we'll go to Excel, tell you that how you can operate Excel, because you can do it by calculator, but Excel is much faster. So I want to show you how we are going to do that. Okay. So there's a video link that you can look at it in case you and this is the old slide, so that means that I contain a proof there. So for those who actually math oriented should look at the video and check out how I do the proofs. Okay, but if you are not going to do any stat in the future, so then you can ignore it. Okay. Now I guess it's good time to look at Excel. Okay. So let me open Excel. Okay. So for the Excel slides, so let me go here. Okay. Excel conveniently give us big P and big F. Okay, and you can do it for your assignment as well. Okay, unless I explicitly said you have to write down the formula, right? Otherwise, you can write down Excel formula and you give me the answer, right? Unless I ask you to do it explicitly. Okay. So the first one is to buy this XNP force. Okay. So here it means that I have n trial, okay, and I want 2 of them successful, and each trial have probably 0.3, okay, and I force at the end means that I have a P, okay. So this gives us what? If I ask a question like the following, just to review, I toss a coin 5 times, okay, each coin would have probability of head is 0.3. I'm asking what's probability that out of 5 toes, 2 of them are heads. Then you can just input this formula. I'm done. Is that clear? Okay. So let us do the Excel to make sure that you understand what's going on here. Okay. So I have a binomial. Okay. I have n. I have p, right? Which is the problem give us this is the case, right? We have how many trials we have, this probability p, each one successful. And I want to say, in particular, I will look at 2 of them are successful, right? So this x is 2, okay? Now the question is, what is p of 2, right? So how likely that I get 2 success out of 5, which each success have probability being 0.3. So all I do is by norm dist, okay, by norm dist, and I have 2 here, x is here, okay, and I enter number of trial and the probability, okay, and then I tell them it is a force, okay, the force give you the mass, maybe as a px, right, it's better. So maybe I just put the formula here, okay, so that would be the formula, and let me save it in case this is the ren. Oh, I forgot to save it. Sorry. Let me save this guy. Excel 14 October 2024. Okay. So this will be the P of X, right? Then the next question, which often we ask is, what is the probability that you have less than or equal to 2 success, right? How likely that I have 2 or less heads if I toss a coin, which means that I have f of x, okay? Then that case will be binomial this, right? Again, numbers is 2, trials is n, and probability is 0.3, and I say true, which will give me the answer. Okay. Okay, so that would be the idea behind this. Okay. Now, since many of you are just sitting there not doing something, okay, maybe I give you a very quick class self-test. What is the probability that you have 3 and 4 success? 3 or 4 success, right? Out of 5 success, how likely that I have 3 or 4 success, right? Means that I toss a coin 5 times. How likely that I have either 3 heads or 4 heads? Okay, I'll just give you 2 minutes to figure it out, and I will announce the answer. Okay, so the question I'm asking is probably that x equal to 3 or x equal to 4. Okay, so try to challenge a little bit, because otherwise you're just sitting there not learning, right? Just a simple exercise. Try. So remember, this question is same as like you have 5 tables, right? Each table have 0.3 probability that the customer likes spicy food, right? The same idea. Remember so I think 2 minutes has passed. I can answer it. So this is considered as, you can do the following, okay? You can separate them, right? Because they're mutually exclusive, right? You can just add them up, right? The probability of an event, right? Axiom 3 tells you can add up. Okay. What is P of 3? Actually, we are done. We already have that, right? This is the answer, right? We just binom this, right? Is 3, 5.3 false, right? If you like, right? And 4 will be just 4, right? And the answer we just add up. Will be just this answer. Is that okay? So I hope that is clear. If the question asks you how likely that, 3 or 4 tables of customer like spicy food, right? Is that okay? I hope you understand. This is following from Axiom 3. In case you want, I just put it other side so to make sure that this is okay. Maybe I separate a little bit, one more line, okay? Is that okay? That is binomial. A little bit smaller. Okay. Is that okay? Of course, I'll upload this Excel file to the backboard so that later you can check it out. Now the next part would be, okay, this already here. I'm not going to talk about that. Okay, you can plot it, PDF, you can plot the CDF as well. I'm not going to do that. You should be able to do the plotting. Okay. Now I look at the Poisson. Okay, it's very same, but lambda. Okay, and lambda is the following, right? It's like, say, in an hour, on average, the 5 customer comes in. What is probability exactly 2 customer comes in? Will be follow from this equation. It's P of 2, right? With lambda equal to 5, right? So let me show the Poisson. Okay. Okay, this is binomial. And I have Poisson. Okay. Poisson. Okay. And the only thing that define Poisson is lambda, right? Lambda is on average period of time, how many event would happen on expectation is NP, right? It's on average in this length of time, how many on average should appear, right? So if I ask every hour you have 5 customer comes in, and we're talking about 2 of them will come in, the probability, right? P of X will be just simply Poisson X mean mu and force. Maybe I always spelled it wrong. It's P-I-S-S-O-N, Poisson. Sorry for the typo. Okay. This with the probability exactly 2 people comes in, right? And usually we are not that particularly interested in this, but rather we're interested in that one, right? We're interested in how likely that is less than or equal to 2 persons to come in, which give us big F of X, right? Poisson distribution, which is X, this, and force. Okay, this gives us the true. Okay, so you will see that would be the problem. Okay, so now maybe I ask this question, okay, to make it more fun. Okay, what is probability that, okay, within the next hour, okay, how likely that you have, say, 3 to 5 people come in, right? So 3 or 4 or 5. Okay, how do you do that? Okay, again, I'll give you 2 minutes, 3 minutes, maybe we have 3 items to work it out, and you can try. So I guess 1 more minute. Okay. See, some people still working. Oh, in case you wonder how this consistent with that, you can calculate exponential negative 5 times 5 raised to lambda x lambda 2 divided by factorial 2. Give the same answer there. In case you wonder what the formula is, this one. Same as your textbook. Sorry, same as your slide. E to the power negative lambda, lambda with power x divided by x factorial. Right? So that will be the formula there. In case you wonder, big cell do correctly, right? So that's why we need to tell you what is the F. Sorry, what is the P, right? The big P is this. Okay. But now we are going to give you this. Okay. Again, a random variable can only be one number, right? So when it's 3, it's not 4. When it's not 4, it's not 5. It's mutually exclusive, right? So when you have OR, addition rule tell us that they cannot be the same, and mutually exclusive, n is 0, right? So that means that it's either you just 3 items add together, right? It's just probability, maybe just I'm just lazy, just like P of 3, P of 4, and P of 5, then I'm done, right? Right? Because add them 3 up, it will be my answer, right? Because that will be the case, right? Because 3 of them, you just add them up, right? They cannot happen at the same time, right? I mean, only one of them is true, if they have the truth, right? Cannot. So this one will be Poisson 3, 5, force, right? So let me copy this formula here, okay? And I'm just being lazy. I just change the 4, and I change to 5, okay? And is it 4? Right, that's correct. Turn out to be very interestingly the same, but for some special reason there, add. That's my answer. Okay. You can see this a bit surprising because 50% is actually to 2 to 5. Okay. And is that okay? So I guess to make it more fun, let me ask you the question before you do the break. You can think about that during the break because I think the break is usually too relaxing. And today we're relaxing day anyway. So let me have fun together. Okay. Let's ask this question. Okay. What is the probability that if you model the number of customers arriving as a Poisson, with probably that you have, say, 5 more customers arrive. Okay. The question is 5 or more. So x is equal to 5 or 6 or 7 or 8 or da 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 da. Okay. What's that? Okay. Remember, I go to infinity. Okay. That the trick is have to use the big F. Think about that carefully, and then we will talk about that after the break. Okay. In the meantime, I hope it's clear what we're asking. Right? You can take a look. But in the meantime, we'll give you the real reply. You can play around with that. Okay. And we have a break of 15 minutes, and then we'll come back to the Poisson. Okay. I see you in 15 minutes time. Walk around to see if any question. You can play around with the question I asked, or you can just relax, sit back, and wait for my solution. But that will be something similar asked in the assignment. So if you know, then you will see. Okay.
Right. It's like said, how, what does the zero here represent? As in, you cannot have zero, I think it's exactly zero. Oh, yeah, yeah, but what, like when you said, when you been to draw a line, what, suppose that it's as a machine that can. Suppose I got. That is according to. And but is that what is that square number? Is that the baseline for determining? Oh, it's like suppose it's 1, the square is 1/1. Also, just literally get the number that's. Oh, that's yeah. Oh, okay. I was thinking like this. That's like this way. Just pick a number there. It's where it's 1. Oh, okay. Okay. Thank you. And it will look like this. And 1 is that this way. And this way. Anything is below 1 will be. And so these are basically the picking. This is the result. All right. It's an F. Okay. That is areas. I thought you meant this is we did like picking this as going sign and evaluating this. Whatever number you pick, and look at how frequent they are. It's more like still. Okay, that's easy. That thanks so much. Nothing new there. Yeah. Yeah, oh yeah, that's perfect. So thank you. 对，所以这个是老写的 n 那个直接把它们 n 车的话，然后 n 个 n 個實個實乜嘢？個實嘅嗰啲情況，點解講錯嘅？即係話咁，但係如果將時間諗成一個比較中意，大家成好多個 second， 好多 second 比較容易計翻，有一個 second 有一個 second， 呢啲 second， 如果人啲時間話咁啲 n 係好大。呢個時間 set 到細個標準，我呢個就係嗰個特別呢個時間有咩發生嘅事？成個標準先做嘅情況下，即係成功可能其實兩成好將呢個時間嘅可以排過好多個細嘅時間，好多個細嘅時間。有個時間段成功嘅，真係每一個時間段有啲一個時間，如果有即係兩個人嘅地方喺度做明講，咁佢最後嘅 P 就係要同佢 P N P 嚟 N 嘅就唔會喺度咁嘅度買呢個諗法。因為個辦公嘅即係話呢段時間係好細，嗰個時間通常會話俾你聽咩嘅，會最關鍵㗎啦。呢個唔係 step 啦，我哋話俾你聽呢個係 follow 乜嘢，咁你發嘅交流真唔夠話做，你同教授我哋會問你呢個要咩點嚟？變咗數學落嚟。我有陣時可能即係我唔需要話俾你聽，我要將自己就係將啲數字就話好錯啦，其實都我啲題目冇話俾判斷啦，俾埋嚟㗎啦，即係呢啲就好明嘅判斷，好明㗎啦。分翻啲咩？你好明嘅，好明嘅，如果唔有陣時我考試冇需要判斷，其實應該要佢應該要佢。抽完打佢，抽完打佢。你辦安票嘅抽打翻佢，你每次標一樣㗎嘛，但係抽完之後打翻佢就你咪抽好抽少㗎，你抽咗就冇咗啦個嘢。買咁咪即係話啲即係即係為咗驚係死驚係堅係，咁咪有機會先問題。咩就係話呢度話俾你聽，都話俾你聽佢就後面嘅幾五好5就話，我哋我抽4件嘅，就如果嗰啲係後面3嘅一個好難對，跟住但係我見到啲色我就開始啲色係需要。知道嘅，但係我哋可能講俾你聽，即係你可以驚，但係我啲唔係驚，即係你可以電話黑咗啦，即係都唔講嘅。佢都係知道個地方其實喺邊度，我跟住我啲我 skip 嘅，我都大，我會擺上睇人 care。你想知道就係睇知嘅，咁啊，你都唔打到嘅。哦，佢只係兩個選項，好似有個佢發市場㗎。True 嘅話定係 false 嘅話 ？True 嘅話，得兩寫。
So let's see. I think the break is over. So let's check out how well we are doing. And there's a question. What is linear power expectation? Very simple. Linear just simply mean the following. The two content in it is expectation of X. Okay, is simply you go back to here. Linear means you multiply by constant, and plus a constant will be just applied it the same way. So simply that is that's linear property. So basically it's just the following, you multiply, okay, a constant and plus a constant, you just multiply the content itself plus. So in application, it simply means the following. We don't need to worry about modeling every portfolio we want to know, right? We just need to focus on individual stock, not even portfolio stock, okay? One stock and then done, right? Or we look at, we need to model stock price. I can model stock return, the same thing, okay? So I don't need to separate model for the stock price and stock return. So that is the linear property. I hope it's clear, right? Just multiply. So suppose I invest a stock, one share or 1,000 share, doesn't really matter. The return of 1,000 share will be thousands of the return of one shares. All right? Or I invest in stocks is X, my bond is B, I can separate them. So that is the main idea of linear. I hope that will be okay. If you still question, you can just left there. Other section are laptop, internet off. So the question would be, I can't check whether internet is off. That's difficult. Unless I have the jamming equipment, which is not legal in Hong Kong. And the concern would be if one cheat, then we have to take all the tests again. Okay. So I don't know how they can block the internet. Probably they have to install some software in your stuff. And to be fair, not everyone have laptop. Many people have iPad. So I guess it's not possible to have that unless everyone would want to pay for an iPad. I mean, have an iPad, have the same iPad, then I can install a software on your computer and make sure that you don't cheat. That would be a massive nightmare. And is it advantage? No, because we are not using the uniform grading. I grade within my class. They grade within there. So I don't see there's an advantage to you. Okay. And also, if you really consider late ad job, you want to drop this class, I'm okay. I can sign it. If you say you want to enroll to the other one because of this, I mean, you can do that. I mean, I have no problem with that. So. Oh yeah, new haircut, yes. Thanks. Do we need to study continuous this normal discipline exam? Well, do remind yourself why I asked you the green boxes, right? If you understand green boxes, which actually the assignment is about, then you're done. And the continuous like chi-square student t will be used later, right? As I said, chi-square is not directly used. We will use T and F. And if you check the handout, you will see they use very often for the rest of semester. Okay, so that should be, and I think you'll be there. You shouldn't need to worry about it. As long as you know the assignment, you know the green boxes, then you're done. Okay. I'm tired. Yeah, this is the middle semester, and it's often the case is very tired. Okay. And I remember one said is, if you're done halfway, you're 90% done, right? So we are 90% done almost, right? Because the rest, you notice, the rest of the semester is that remember some rule, some algorithm. There's some problems and remember the rule to apply. So I don't think there's new math behind from now on, but there's no particular new knowledge. Okay, I hope that would make you feel happier. Yes, you will do the F test. We will do it. And ANOVA, we will do F test because comparing variance, as I said, right? F test is comparing variance. We'll use ANOVA and regression. That is the thing that you want. You want to pass? I think you will. As long as you do the assignment, you do your project, then you attend the exam, then shouldn't be. I mean, I guess if you do all the rest, you should get a pass, right? Shouldn't be an issue there. Yep. We know today, a little bit cloudy, yes. Yes, we have a very nice description. T is very close to normal, but the tail is fatter, so it's like a bigger kurtosis. Still the same, just like much fatter. This is a very nice writing. So this is, as far as we know, this is what we need. Okay. Actually, this is what we need to remember what's T. Okay. We don't need to care about this. That is same as mean zero, and then it's fatter than normal. That is what we need. Quiz. I hope it's not my class, but I think you're studying quiz for other course. But hope you still pay some attention to our class. The speed is appropriate, I think. Most likely you can follow a little bit. Okay. Let's wait until we read the rest before we go to the video. What do you give to a sick lemon? Lemonade. Okay, that's good. Oh, that's a good one. Fresh cut. Oh, I think it's really good. Oh, yes, fresh cut. I cut it yesterday because my son cut it, and I said, okay, since my son do the haircut, I think it's a quick cut, Japanese style. My son got it, and I can, okay, why don't I get the same? Okay, so we only have one fun. Let's see. So let's see what the fun is. Oh no. Oh no, it's not copying. Copy, copy, copy. No. Copy, no. Copy, eh? Copy, 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 copy. Okay, this seems to be interesting. Let's see. So I guess what they said is very nice and cheap and very good Japanese seafood, and highly recommend. So for those who feel tired, who feel depressed, maybe it's a good recommendation. You can try there. I think it's not too expensive. It's reasonable price. I think you can try. Okay, it's in Tsim Sha Tsui, so we can take the subway all the way there. Shouldn't be too far away. Okay, there's a lobster tenfuro, so try if you want to. I don't know. I mean, can't be from my recommendation because I haven't tried it, but it's from your classmates, so enjoy if you want to. So first we look at this again. Okay, this how can you do the calculation that to do it? Okay, so how to do that is we will invoke what we call complement rule, because you can possibly, of course, you can add 5, 6, 7, 8 up to infinity, but no one have time to go to infinity, right? But we do notice that we can consider a case where it is probability x equal to 0 or 1 or 2 or 3 or 4. Okay, this is what we know, right? We know this guy. What this guy? This guy is what? Just simply f of 4, right? F of 4, right? And f of 4 is simply Poisson distribution 4 and 5 and true. Okay, and this is the answer. Okay, and you just simply take one, subtract from that, that's complement rule, then we're done. Okay, so that would be okay. So that is the formula. Maybe just equal to this. Okay, so that would be my solution. Very simple. All right. So this will be something similar. You will see the assignment. Okay. Just only trick part is up to 4, not to 5. That is only part that I have to be careful. Right. Less than or equal to 4. Right. 5 is not included. So this is the only part that slightly a little bit complicated, but otherwise shouldn't be an issue for you. Okay. So. Oh, sorry. I don't know why there's a sound over there, but. So I hope this gives you the idea how to do Poisson. Okay. And hypergeometric, right? Remember the question is we have 30 items in the warehouse, and out of 4 is defective items. Okay, which means that 26 are good, right? For 4 bad. Okay. The question would be if you try to draw 6 items out there, right? We draw 6 items, we don't put it back, right? We take out 6 items and check each one. We are asking probably that 2 of them are bad. Okay, let me repeat the question again. We go to the warehouse. We are told that we have 30 machines, and the client told me that your auditor, 4 of them are bad. Okay, and then okay, let's try to check out this right or wrong, and then randomly pick up 6 machines. Okay, run all the program, and what's probably 2 of them turn out to be defective, right? That is a question. Okay, do you know that this is very similar to binomial, right? Binomial will be you check, randomly pick, you can pick the same item, but exponential will not do it, right? So that is it, right? This is hypergeometric. Okay, but in case you want to do it, then let's do it. Hypergeometric. Okay. And the way we do is, right, is N, A, N, X, and P of X, right? We have 30 items. Our 4 is good. And we take 6 items out. We want to know the probability 2 of them is actually bad one. Okay? And do not hypergeometric, we just take it 6 altogether, right? And that simply is hypergeodis number. We have X there, sample here, population, this guy, and pop, and then false. Let me see, what's the problem? Is NNA, is it something wrong? NAN, oh, sorry. It's 3, 2. Okay. So you input the A and then N. Okay. So that is the answer. Okay. And F of 2, right? You can ask the probability that actually 0 machine is wrong, or 1 machine is wrong, or 2 machines is wrong, right? Will be just do the same, right? X there, A there, A there. I just go up one by one, right? So that's very simple. Okay, so that would be, not surprisingly, right? 98% is within 2, right? So if you audit, actually, we don't do it now, but you can actually see you can be used apply in auditing, is because if your sampling give you 3 machines is wrong, what do you conclude? Is it possible? Almost not possible, right? 2% of chance that happen to be there. So you might likely conclude that your client is lying to you. It's not that only 4 machine doesn't work. It should be way more than 4. Okay, so that is actually how we use the hypergeometric. But we stop here. We don't talk about application audit, but you can see you can apply the audit, right? If say you have 4 machines or 5 machines wrong, then highly likely that your client is not honest to you. Actually, it's more than 4, right? That is actually this is how we apply this when you audit, right? Or you can say this is how government or quality control, right? That's how they do, right? You claim accuracy rates. This is how you can test, right? Is that okay? I mean, you will do more assignment like this when you go to the assignment 2, okay? If that's okay, I would like to draw your attention to a continuous, okay? And for continuous, as I said, it's slightly troublesome of the fact that the notation they use is the input is 1 over lambda instead of lambda. Okay, so that's why 1 divided, because it depends on textbook. Because 1 over lambda is the mean, so just put the mean there, right? It's the mean of the time that is arrival. Okay. And actually, some of you ask why we need small f. small f is to illustration. And for all calculation, you always use the big F. All right. So this question will be the following, right? Exponential is model time until something happened, right? When we say it took 20 minutes on average for something to happen, so our lambda is 1/20, right? Because lambda actually is the Poisson idea, right? In our notation. Okay? So in this exponential, true here means that on average, you took 20 minutes for something to arrive. I'm asking how likely that it happened in 10 minutes time. Okay, so that is the exponential dist 1/20 true. Okay, so let me do it to you. Exponential. Okay, exponential with lambda, okay, is 1/20. Okay. Oh, so when you have this problem, you have to with the general first. There's a number there. Number first. Yes. Okay. Now x is 10, right? So remember, I have on average 20 minutes, right? And the question, the f of x, that's what we care, right? Is exponential, this guy. Remember, it's 1 over this guy. Okay, the lambda we have is only lambda and then false and true. Okay, so that is why? Yeah, wrong. Why? Let's see if I did something wrong. 10, 20, true. Did I do something wrong? Let me check, sorry. Oh, okay, okay. I just put B2, right? Sorry. Yeah, I think that's right. Yeah, just put in the lambda there. Oh yeah, yeah, right. That's right. Yeah, I didn't 1/. Yeah, so that would be the. Oh yes, I see. I see why it's wrong because lambda is 20 here in my model, so I should be 1/. That. I'm sorry that. Okay. And probably you see why is lambda is more direct, right? Lambda is 20 minutes and I take 10 minutes, so that's why I use this notation. All right. So just to make it more fun, maybe ask this question, okay? On average, you take 20 minutes to wait, right? For, say, suppose wait for a doctor, wait for service. What's probably that it would take like 30 minutes, right? What's the probability that x is more than 30? That's a question 1. Question 2, maybe more fun, okay? What's probably that it would take between 20 to 50 minutes, right? Maybe more fun to ask this question. Maybe 6, right? Between an hour and half an hour, right? I think it more sense, right? The first is asking how likely that is take more than half an hour. The second question is how likely that it take Between half an hour to 1 hour. Okay. Is it meaningful? Right? Does it make sense? Right? This is the question that we ask. Okay. Maybe I give you 2 minutes to figure it out. It shouldn't be too difficult. Okay, I can see most of you have done. So let me show you the answer. So this is simply f of 30. And this 1 minus this guy will give you the answer, right? Use the complement rule, right? So f of 20 is exponential 30, 1 over 20, and false. So true, right? So it will be 70% should be within an hour. So we take one subtract from that. That should be the answer I have. Okay. So I hope this answered the question that we have, right? Question. Is that okay? I hope that will be clear. Now, the thing that I do is I need this guy and I need this guy as well. Okay. And then what I need is this. And the answer will be this guy minus this guy. Reason shouldn't surprise you. I have exponential here. Go down. This is f, right? X here. And I want something between 30 to 60, right? So which means I need this area, red area. Okay? The red area is somewhere between 30 and 60. That's a small f, right? And big F give us what? All the area on the left. Big F give us area on the left. And the small f. Okay? So what we're going to do is take the orange area, which is this guy, minus the green area, which is this guy. Orange minus green is red. Is that clear? Let me repeat. Orange minus green is red. And the big F gives us the area on the left. Under F, okay? So, and I have access to the orange, access on the green, I have red. That's always we do. Actually, we do all this kind of calculation for the semester. I mean, unfortunately, this is the thing we do for the rest of semester. Maybe too simple or maybe too difficult, as you say, depends on how we understand what's going on there. But there's always like this all the time. Okay, it's a kindergarten style. Okay, is there any question? Okay, so if you are following this idea on average, most of the time you got handled in first half an hour, right? Then you have to wait for 1 hour. It's like 70%. Okay. Is that okay? Is that okay? I erase this one if there's no question. Okay. Now, finally, let us go to normal. Okay. Normal, again, we don't need the small f. We always need the big F, right? Small f just to illustration. The idea how to draw the graph to the calculation. And now probably you see why I talk about small f. It's not for calculation, but to illustrate the idea how to use the big F to do calculation, right? Big F will give it the area on the left-hand side of the small f. Right. So this is the last bullet point, right? Is asking I have the mean of 20. Okay. The standard deviation is 4. Okay. Asking the probability that x is less than 16. Let me draw again. What does that mean? It's just like a bell curve. It's standard bell. Okay. And you were told that the mean is 20. Wait, which is the mu? Okay. The standard deviation, okay, is 4 here. Okay. So what this calculation gives you is area on the left, right? This x, right? This is the f, right? If you want to look at this is a small f here. Okay. And if you enter this into Excel, which we'll do soon, give us this number. But what does the number mean? Means if you look at 16 here, right? 10 is here, 16 is here. This area is 15%. Okay? So let me repeat, the big F give us the area of the left-hand side of the F. Right? This is the answer. Okay? Is that okay? Then let me do Excel, right? To make sure that we're on the same page. Okay? So normal. Okay? And you can see I don't need to go to standard normal because already that will be the Excel conveniently tell us mean is 20, right? And the sigma, which is the SD, which is 4, and x is 16. Okay? So I want to calculate what is f of x, right? So it will be norm this. You put x, you put mean mu, SD, true. Okay. Okay, that is how you do, right? Norm this, x, mu, sigma, true. Okay, so that is how you get 0.158, right? So 60% is below 16. Okay. And as a quick illustration, ask yourself, what is the probability that this x is less than, like, say, I don't know, maybe much more fun, right? X is more than 21. Ask yourself how to calculate that. What is probability that maybe 15 x 23, say, okay? How do you calculate these two, okay? These two are the important calculations that you know how to do, okay? I give you 2 minutes to try. Please try. I mean, because if you're just sitting here not doing, then it's not going to learn. Okay. If you don't want to try, at least keep paying your classmate how they do it. I mean, otherwise you're not learning, right? Active learning requires some action from you because I will ask you to do it in an assignment. So if you don't know how to do it, then you have a problem. I mean, you have to ask the TA, right? I'm not going to help you. I mean, your TA is going to help you. Okay. So just try to test yourself. You understand that. So to give you some hints, first you calculate this guy. Right. And you would calculate this guy. And okay, if you know how to calculate them, then you should be able to do the question. Okay. Let's do it because I see many people already waiting for me. So how do you do that? This is just F22, 21, right? So just basically norm this 21, I think 20 and 4 and true. Okay. So do remind yourself what am I doing here? This one gives you the following, right? This one gives you this 20, right? And give you 21, give you the red area. Why we need to calculate this one? Because we are tasked to do more than 21, which is blue area. Okay? And blue and red must be add up to 1 because we want the area on the right-hand side of the F, right? More than that. But what we have, the big F is the area on the left, right? Total must be 1. You take the area on the left, from 1 from that, area on the right. Okay? You want the blue. Blue plus red is 1, right? Complement rule. Okay? So 1 minus. Okay? I'm sure that for many of you that is too simple, but we will be working on this throughout the semester. So it's better that you know now. If not, then you will know later. Okay? Is that clear? The red one is the, right, is the line over there. You subtract it. Okay? Let's do this again. How do we do that? This is F23. Just norm this. Okay? 23, 24, true. Okay? And this is norm this 15, 24, true. Okay? And you take the subtraction here. I'm done. Okay? So again, you probably ask, hey, what am I doing? Okay? Let me show you again what am I doing now is to draw a graph again. Okay? Let me draw again. Okay? I have blue line here. Okay? And this is 20 here. Okay? And the question being asked to us is F, right? Is the area between 15 and 23, okay? Which we want the area red. How can we do that? How can we do the red area? Somewhere in the middle, but we have access to the area on the left by the big F function, okay? So we first calculate the area on the left of 15, okay? Which is 10%, okay? F of 15, right? That's how we do it. The second step is looking at the area on the left of 23, that's the green area. Okay, the green include everything all the way up to 23, which is 77%. So green minus orange is red. I hope you can see that. Okay. I know it's stupid, it's simple, but we have to make sure everyone knows because this is something we do for the rest of the semester. Okay. Unfortunately, it's that simple. Okay. The only new thing we learn for the rest of the semester is how to apply this, right, before the step. Okay. We will add some step and then go to this one and then you do it. Okay. We'll do the order bell, either T bell or the normal bell all the time. Okay. Do some F, but mainly the T and the standard normal. Is that okay? Is that clear? Is that okay? Is there any question? I hope that should be fine. Okay. Now, I would like to draw your attention to the very last thing we're going to cover in this class. Okay. Okay. Is the norm inverse. Norm inverse. Okay. Norm inverse is to go back. I give you the area on the left was X. Okay. So the question would be the following. Okay. It's asking what is the probability that X less than X, okay, is equal to say 0.6. What is the small x such that this would hold? Okay. In the other words, okay, we're interested in the following question. The green here, we have 20. Okay. My question is, okay, let me ask the following. I tell you the area is 0.6. Tell me what's this number. Ooh, just reverse what we do. Okay. I tell you the area on the left hand side. What is exactly number there? Okay. So we will use the very simple. We'll use the norm dot inward. Okay. Norm dot inward. So the formula will be norm dot inverse. Probability is 0.6. Okay. Mean is 16. Sorry, mean is 20. ST is 4. And that's it. So it tells me that this number is 21. Okay. 21 left hand side is 0.6. Okay. Is that okay? So this, we will often ask this again. Okay, you will notice. Is that okay? And if that's okay, then I want to very briefly talk about the other two functions, which I'm not going to illustrate right now because we do it later. Okay, is the same thing with the chi-square and chi-square inverse, right? If we place a norm, it's normal. Chi-square is the same to chi-square, but we never use this one, don't worry. And if you have T, it's T, okay? But T will have degree of freedom df, which we'll define later. When we use it, we'll talk about it. But don't worry about it. I just show you there's a function there. We'll use it later, okay? And the F distribution with the same thing with M and N. D1 is the denominator, D2, DF2 is denominator, right? DF1 is numerator, okay? Don't worry. This, I will talk about that more clearly later, okay? So for the remaining 4 minutes, okay, I just use it quickly to review what we have done because we've done everything in the first half of the semester, okay? For the rest will be estimation, hypothesis testing, and so on and so forth, okay? So let's review what we've done so far in the first half of the semester because midterm already, right? We don't have midterm test, don't worry, just midterm. The midterm is middle term. So the first thing we cover is chapter 1. All about is, just go back a little bit quickly, right? Descriptive statistics, right? So what we learn is how to use number to describe data. The mean, median, mode as a single way to describe data. You tell me data, give me one number to describe it, mean, median, mode, right? And then next we talk about 5 different ways to talk about the dispersion, right? Is range, interquartile range, variance, standard deviation, and coefficient of variation, right? And after that, we learn 2 types: shape, kurtosis, and skewness. Okay, and we talk about how to relate to variable by covariance and covariance coefficient. I think you know it very well from assignment 1. right? And after that, we talk about probability, right? And here we learn how to define probability from classical definition is you repeat many experiments many times. It's a ratio, right? Do remind yourself how we define probability, right? That is from you do a lot of experiment, okay? And that tell us from physics or from engineering perspective how probability being constructed, right? This is how the math with the real world, right? But by that we can't go very far, right? Because a lot of things there's no experiment can be done. So come from other theory, okay? Come from many things that we have to define based on axioms, based on assumption. So there's 3 axioms we have need. First one is axiom 1 said anything is between 0 to 1. Axiom 2 is sample space is 1. Axiom 3 we have used all the time. If mutually exclusive, sum of the probability of all the part is as a whole, right? It add them up, it's fine, okay? And then based on this, we have many rules, right? Complement rule, which you use today, right? Area left to right, sum to 1, right? We also have the rule like the addition rule, right? We also have the rule, probability rule, and odd ratio we define, right? Because remember, odd ratio is a alternative definition of probability in the old days, right? But that is from 0 to infinity, right? And then we learn more advanced concept is called condition probability. Why we need that? Because once we define that, we have a very important application. It's called Bayes' theorem, right? That's the most important thing. One of the things we learn in the first half semester, because that's how we learn things. That's how machine learn things. One of the way, right? Machine learning thing can be very complicated, but Bayes learning is the most basic thing, right? We have prior, which is PA. Once we learn new thing, we call PA given B. Okay, I think you do it in assignment as well. Okay, and the assignment 2 will ask you to do what we covered today, right? The whole random variable, right? Go take a look. Will be assignment 1 Q1, and we tell you the distribution. Okay, and some of you asked me at the last remark is you may worry about I have a question. You have to decide what distribution you are. In general, you should able to do it. But for our assignment, for our test, we are not required to discern, to distinguish which apply. You will be told what apply there. Okay? So I will see you on Wednesday. This assignment will do in 2 weeks' time. So will be 4th of November. Okay? The quiz also will be released as well. So see you later. The quiz is unmarked, okay? You can just do whatever you need, okay?